Welcome to the solution for homework set number 3 for ECE 321 Analog Electronics. In this homework set, we're looking at designing active filters. Now, in embedded systems, you'll be designing filters using software. In this class, we're designing filters using hardware. To start with, a filter is a circuit where the gain depends upon frequency. So for example, if I have this transfer function that represents a differential equation, to determine what it is, cross multiply and then multiply out. S squared means the second derivative of y, s means the first derivative of y, and y just means y. So here's the differential equation relating x and y. Or if you prefer prime notation, that's the same thing. Y prime means the first derivative, y double prime means second derivative. Oftentimes prime notation is used because it's a lot easier to write. Problem, or part B, says find the output if the input is a constant and a sine wave. To do that, treat that like two separate problems. This uses superposition. Superposition says if I have a function of a plus b that's equal to the function of a plus function of b. Filters are linear circuits, meaning I can do this trick. So I've got two terms, DC and AC. Treat that as two separate problems, the DC problem and the AC problem. So at DC, when x of t is 4, here's my input. The frequency at DC is 0. E to the 0t is 1, so that's 4 times 1, constant. This is the gain everywhere. The gain at DC is the function evaluated at s equals 0. Here's the input at that frequency. Multiply it out, I get a number. So that's the DC term. AC is right here. The input for AC, the second term, is 5 cosine 7t plus 6 sine 7t. The phasor representation is 5 minus j6, 5 cosine, 6 sine. The frequency is 7 radians per second. This is the gain everywhere. All I care about is what's the gain at 7 radians per second. This is the input at 7 radians per second. Multiply it all out, I get a complex number. Real part means cosine, minus j means sine. The total answer then is your DC term plus the AC term. So there's y of t. And as a sidelight, one mistake that people oftentimes make is they'll take this complex number, add to that complex number, and get 11.6 or 15.6. You can't do that. The reason being is the second one is at 7 radians per second. The first one's at DC. These don't simplify. I can't add those two together and get 15 or 7. They're just different frequencies. So when you do it, remember, each part is a different frequency. You can add them together as sines and cosines like this, but they don't simplify. Problem 2 is a filter design. Come up with a filter to implement this transfer function. In this case, I've got real poles. That tells me I can use an RC filter. So one way to implement it is like this. The DC gain, if you plug in s equals 0, the DC gain is 3.4. I can't get a gain of 3.4 with an RC filter, so I need an op amp. So I'll add an op amp to provide a DC gain 3-stage RC filter. And one way to design it is pick your R and have R go up by 10 times for each stage. That reduces the loading. It's not 0, but it's almost negligible. Then, 1 over RC is 2, that's this guy. For this one, 1 over RC is 6. For this one, 1 over RC is 12. Solve for C. And I need a gain of 3.47, so add a non-inverting amplifier with a gain of 3.47. Again, for non-inverting amplifier, the gain is 1 plus R2 over R1. So this is a 2.4 to 1 ratio to give a gain of 3.4. So there's the solution. Problem 3 is repeat when I have complex poles. In that case, what I'm going to do is I don't know how to do a circuit with 4 poles, but I do know how to do a circuit with 2 poles. So rewrite that in 2 parts. There's the second order system. Here's the second order system. And here's what the answer is going to look like. To solve that, 1 over RC, well, R is kind of arbitrary, so let's make this 100K, that 100K. 1 over RC is 3, so solve for C, and I get, let's see, 3.16. 3.16 microfarads. Same thing here, 3.16. To get 71 degrees, I have 3 minus k is 2 cosine of 71 degrees. Gives you 71 cosine 2 times 3 minus 2.34. So k is 2.34. Pick this. I'm going to pick 100k. And this is 134k. So the ratio is 1.34 plus 1 gives again 2.34. That's this stage. The second stage, let's do that in orange. 1 over RC is 4.4. So pick this to be 100k, 100k. 1 over RC is 4.472. So C is 2.23 microfarads. Let's see, 3 minus k is 2 cosine of 63 degrees. So 63.43 cosine 2 times 3 minus 2.14. So make this 100k. This is 114k. When I'm done, the total gain is 2.34 times 2.14. So the total DC gain is 5.00. This is supposed to have a DC gain of 1. Up here, if you analyze it, the total DC gain, well actually at DC, that's 500 over 10 over 20. DC gain is supposed to be 2.5. The actual DC gain is 5. So this isn't actually y, this is 2 times y. I have the DC gain is twice what it should be. One option is to reduce the gain, add a gain of a half at the circuit, or just live with it. Typically, I'm going to have some other circuitry amplifying the signal. This guy gives me gain of 2, free of charge, so I might as well use it. And that just means the rest of the circuit means less gain. And I can model that just by saying the output isn't y, it's 2 times y. Problem 3, or 4. Give me a filter with this gain versus frequency. So if I look at the transfer function, I've got poles and zeros. If I'm close to a 0, the gain is 0. Close to a pole, the gain is large. So I know right away I've got a 0 gain at 0. The numerator has an S. I've got a pole right here. So there's a complex pole at 5 radians per second. So the complex part is 5 radians per second. There's the second pole with a resonance right here. So there's a second pole with a complex part at 14.8 radians per second. To get the real part, go down by 0.7, down by the square root of 2. That's right here. That distance is about 1. So the real part's about a half. Again, the bandwidth is double the real part. Over here, go down by 70%, or go down to 0.7 times the peak, down square root of 2, down 3 dB. This width is about 2 radians per second. So the real part's 1. And then there's a gain on top. To find that, what I can do is match the gain at some point, or in MATLAB, calculate the gain versus frequency, find the maximum. The maximum should be 5. So pick case, the maximum gain versus frequency is 5. If I try that in MATLAB, same thing. Here's my frequency, there's my 0, there's my poles. There's my filter. Pick K to make the maximum 5, and K is 974. So here's my filter. If I plot that in MATLAB, that looks pretty much like the other graph. Problem 3. Or 4, whatever problem that was. Problem 5 is come up with a filter of this form that has roughly this gain versus frequency. This is where the MATLAB program fminSearch is really useful. I'm going to guess A, B, C, D, E, and that'll give me some filter. Take the difference in the two. Add up the sum squared difference, and that's how good my filter is. If the difference is 0, I nailed it. That's the right filter. How close can I get? Given the constraint, I only have 5 parameters to play with, and they're in this form. So to do that, I'll write an M file called homework3, completely original name. I'm going to pass Z, and that's interpreted as A, B, C, D, E. Here's what the gain should be. And I did that as a piecewise linear function. For frequencies less than 1, or less than 3, the gain is 1. For frequencies between bigger than 3 and less than 6, it's a straight line. And so I came up with an equation for that straight line, which is what this is. 1.8 minus 0.267 times omega between 3 and 6. That's my ideal filter. Given A, B, C, D, E, here's what it really is. Take the difference in the two, return the sum squared error. And in MATLAB, I can try that. What is homework 3? And again, this is a subroutine. If I do this, I get an error message because I have to pass it 5 parameters. If I try to run the subroutine, I get an error saying you can't run subroutines. You can call them, but you can't run them. Let's call it, passing the numbers 1, 2, 3, 4, 5. And what that did is that just called the subroutine, passed it 1, 2, 3, 4, 5. The red line is what the filter is. The blue line is what it should be, and says that that's not horrible. The sum square difference 237. Can I do better? And what I would do is, let's put a pole at -1, pole at -1 plus j3. So that'd be the s squared plus 2s plus 10. And another pole at j5, s squared plus 2s plus 29. There. Better. Now the sum squared error is 30. Can I do better? Well, I can guess again, or let MATLAB guess for me. Let's get this out of the way. I want to minimize the function called homework3. My initial guess is 1, 2, 10, 229. And MATLAB is going to sit there and play with those numbers, try to reduce the sum square difference, and it plots the results as it goes. Plotting really slows it down, but it's kind of fun to watch. And MATLAB actually does a really good job at filter design. That looks pretty good. When it's done, it'll kick out a number and the sum square difference. What that means is this is the numerator is A times C times E. There's the denominator. There's A, B, C, D, E. So here's my filter. On problem 6, once you get the filter, design a circuit to implement it. Again, this is something I don't know. I don't know how to do a 5th order filter, but I can do a 1st order filter. That's an RC. I can do a 2nd order filter. I can do a 2nd order filter. So I'm going to do 3 filters cascaded. The first one, if I pick R to be 10K, C is 55 microfarads. The second one, pick R to be 10 times bigger to avoid loading. R is 100K. Whenever RC is 3, C is 3.2 microfarads. From the angle, I get a K of 2.1. The third one, the amplitude is 4.9. Give C is 2 microfarads. From the angle, I get K. So here's my circuit. There's my first stage, my RC. To avoid loading, I made this 10 times bigger. There's the second stage, complex poles. There's the third stage, complex poles. In Circuit Lab, I can check that out. So if here's my circuit, what I would do is I would do simulate. Let's do frequency domain. I want to vary the guy on the left, that's V0, starting from 0.01 to 100 Hertz. The parameter that I want is, let's look at the output, V2, that's off the screen. There it is, V2. And I don't care about phase. Some people prefer dB. I personally prefer magnitude. Pick your favorite. Run. And that'll show you the gain versus frequency. If I zoom in on this part of the graph, you can kind of see the gain is roughly flat, then it drops off, then it goes to 0. That matches up with what MATLAB calculated somewhere. Okay, with what MATLAB calculated, there it is. They're kind of similar. This is on a log scale on the x-axis. This is a linear scale on the x-axis, but kind of the same. So that kind of tells me that that looks like the right filter. We just did that, and we're done. Okay, so that is homework set number 3 for ECE 321.